Hello everyone and welcome to Lecture Today. Today we're going to start by discussing some more basic differential geometry of curves and see a couple different applications of this as we kind of delve deeper into the differential geometry of curves in 3D space. And you'll recall that we left off having discussed a number of different topics, but one of the main things we defined and introduced was the so-called Frenet frame, or Frenet triplet. These are three vectors: the tangent vector, the unit tangent vector, the unit normal vector, and the binormal vector. This triplet is sometimes called the fundamental trihedron, and basically can be defined at any point along any curve. So recall that. If we have a parametric curve in three-dimensional space, what we're saying is that at any point on the curve, say this point right here, or this point right here, we can uniquely define the tangent vector, the unit tangent vector to the curve, the unit normal vector to the curve, and the binormal vector to the curve, which is perpendicular to the original tangent vector and normal vector. In certain texts, in certain applications, we term what's called this plane right here. So we term that the plane that's spanned by the tangent and normal vector, the oscillating plane. So this oscillating plane is spelt as and this is sometimes a very useful idea for discussing the differential geometry of curves. So you can kind of think of the tangent vector as going along the curve, and then as the tangent vector goes along the curve, and the curve possibly twists and turns, the oscillating plane will rotate as the curve twists and turns. And today we're going to try to understand this a little bit more in depth and see how we can kind of apply this as well in various different scenarios. So what we'll look at first is a visualization of this plane for a very special example. It's a little bit complex, We'll need to first describe where this parametric curve is coming from. We'll consider the following example. R of t is equal to, and we'll say the x component is going to be cosine of omega t times r plus r cosine of alpha t sine of omega t times r plus r cosine of alpha t, and then lastly r times sine of alpha t. And we will plot this out for t from 0 to 4 pi. So to help us out, we'll open up the GeoGebra plot, the GeoGebra plot of this curve. And I've also plotted on the GeoGebra plot a nice visualization here of the tangent plane, and then the tangent vector, the unit tangent vector, the unit normal vector, and the unit binormal vector. This curve has a number of different sliders to it that each correspond to one of the parameters in the curve. But as you can see, we'll play this animation. As you move along this curve right here, you end up getting that the tangent vector, the normal vector, and the binormal vector all behave exactly as we predicted they would based on the last lecture. And if we go through, we can even show the oscillating plane if we want to, and how that changes as we go through this process. So you see the oscillating plane, the plane that goes along the normal vector and the tangent vector oscillates as such as you move around this this curve. This is a very, very kind of cool diagram. You see that if we have a number of different controls over the different parameters here, and changing these parameters like alpha and omega end up giving us slightly different forms for a parametric curve. And some of these forms will hopefully help you see a little bit where this parametric curve is actually coming from. If we move this over a little bit, we can see this a little bit better. I'll give you a second to kind of guess where it's coming from. It might help if I maybe make this big R right here a little bit bigger. This should hopefully help you see a little bit better where this parametric curve is coming from. So we'll increase alpha a little bit, and then increase omega a little bit. Right, so this parametric curve is directly coming from the surface of a torus. If we plot the surface of the torus with this parametric curve, we can see very, very clearly that this curve is essentially mapping to the top of the surface, no matter what the value of alpha or omega is. And the value of alpha and omega is actually giving you, in some sense, the number of rotations, or the frequency of rotations around both the large circle of the torus and the small circle of the torus. And so this is what these things are controlling, and you can see that very, very clearly, I think. So this is a very, very cool example, and we can use this for all different values of r. You can shrink r to a very small value, make big R very large, make the smaller radius parameter very, very small or very, very large, depending, and you'll get a different curve each time. But the point here is that we can clearly see that the tangent vector, the binormal vector, and the normal vector are all acting like they should. And what we want to do is kind of get a better understanding of exactly how these vectors are related to one another. So we'll start with the simplest relation, and that was actually with the definition of curvature. So first off, we're going to assume, just for ease of calculation's sake, that we have a curve that is parameterized by arc length. So assume that R of S is a curve parameterized by arc length. S. So we have a number of different nice computational simplifications which come with that. Specifically, one of the very nice computational simplifications is that we don't have to worry too much about some arbitrary parameterization T. And one of the big nice ones is that R prime, which is the derivative with respect to S, is just equal to the unit tangent vector. This is probably the fundamental thing of it, is a fundamental piece of importance here. If you don't remember why that is, it has a simple explanation. I mentioned this last lecture. The main idea is that remember that the velocity is defined as magnitude of itself times this unit tangent vector, where the unit tangent vector is just the unit vector pointing in the direction of the velocity. But recall that this just means that this is the velocity vector is the same thing as dr dt, which in terms of the s derivative is, or the arc length derivative is ds dt dr ds. And we proved by the definition of arc length last lecture that ds dt is in fact equal to the magnitude of the velocity. Right, these are the same thing. Therefore, in this vector expression, these two things cancel out, the two scalars, and we are left with the fact that the unit tangent vector is in fact equal to the derivative of position with respect to arc length. This is a big thing for us and is one point of very, very nice simplification. The other simplification that we have is that last lecture we defined what's called the curvature. In this case, we'll just deal with curvature as a function of arc length. The definition of this last lecture was that curvature is the magnitude of the rate of change of the unit tangent vector with respect to arc length, or the total amount the unit tangent vector is changing with respect to changing position on the curve. And this is a very, very intuitive, nice idea for arc length, and why it's why this is the natural definition for arc length. So what this means then, we recall that dt ds, the vector dt ds, was used to define the unit normal vector. If you remember the definition of the unit normal vector was defined as the derivative of the unit tangent vector with respect to arc length divided by the magnitude of this derivative. And therefore, so by the definition of curvature, the magnitude of the derivative of the unit tangent vector is going to be 1 over the curvature as a function of s. And so therefore, if we just multiply both sides of this expression by the curvature as a function of s, we have that an alternative description for the derivative of the unit tangent vector with respect to arc length is the curvature function multiplied by the unit normal vector. And this is actually called the first Frenet formula. I'm going to have 3 separate Frenet formulas. This one is going to be number 1. Because this is giving us a fundamental relationship between the rate of change of one of these vectors in the Frenet triplet, the Frenet frame, and the vector itself, along with the curvature. For the next Frenet formula, we're going to have the following thing to think about. We want to think of how is the binormal vector changing along the curve. And this is actually going to lead us to another relatively simplified formula similar to one up here. What we want to do is take the derivative of this vector b. Right, this is the best way to find the rate of change of the binormal vector as we move through the frame. So to do this, we have to remember the definition of b. B hat was defined as the cross product of the unit tangent vector with the unit normal vector, the curve. So the rate of change of the vector b, or dbds, this is the rate of change of the binormal vector with respect to arc length, is the s derivative of the cross product of t hat and n hat. And we showed last lecture the property of the derivative of the cross product. It follows the normal product rule. So this is going to be dt hat ds cross n hat plus t hat cross dn hat ds. This is just the product rule applied to the cross product. And using what we know, well, in some sense, you already know what this is going to be because dt hat ds, the derivative of the unit tangent vector with respect to arc length, is really just the definition of kappa times the normal vector. This is kappa, the curvature, times the normal vector, cross product with the normal vector. So this first term right here is going to be 0. And then that leaves that the derivative of the binormal vector with respect to arc length, the rate of change of the binormal vector as you move along the curve, is going to be equal to the unit tangent vector cross product with the rate of change of the unit normal vector with respect to arc length. And what this means is that we can conclude some very important things here, because this dB hat ds is the rate of change of the binormal vector is in fact equal to the cross product of the tangent vector and the rate of change of the normal vector. We can conclude the following result. Right? We can conclude that this dB hat ds must be perpendicular to the tangent vector, the unit tangent vector, and it must be perpendicular perpendicular to the derivative of the unit normal vector with respect to arc length. So we'll use that result in a little bit, but using a similar logic to what we did for the normal vector last lecture, recall that the length of the binormal vector is equal to 1, because the dot product is equal to 1 with itself, because it's a unit vector. And if we take the derivative of this expression, we end up getting that two b hat prime dot over the b hat is equal to 0. So dB hat ds is in fact also perpendicular to b hat. So what that means, because dB hat ds, or the binormal vector, as derivative, is perpendicular to both the unit tangent vector and it is perpendicular to the unit binormal vector, the only direction in which it can point, it's perpendicular to both t hat and b hat, so the only direction it can point is the n hat direction. And what we do is we exactly define this to be the following. We define it to be tau times n hat. And this is the second, actually we'll label it the third Frenet formula. And we'll see why in a second. Where tau is what's called the torsion function. Which essentially gives us a measure of how much the oscillating plane is oscillating. It's exactly defined as the dot product of this derivative of the binormal vector dot product with the normal direction, and it gives you a measure of how much the oscillating plane is twisting along the curve in the normal direction. So this is, we have the first two, or I guess the first and the third Frenet formula. What we need is the third and last Frenet-Serrat formula to get a complete picture of how nice these equations actually are, governing any nice enough curve in three-dimensional space. So in order to complete this last step, what we can do is we look at, we know that, remember that the unit normal vector b hat was defined as the cross product of the tangent vector with the normal vector, and these vectors are all orthogonal to one another. So therefore, using our nice property of the cross product, we can actually cycle this a few times, and we also have that the normal vector will be equal to the cross product of the binormal vector and the tangent vector. This is from our properties of cross product chapter. And we can use this very nice fact to look at obtaining the last equation, the second Frenet formula, which is for expression for the derivative of this normal vector with respect to arc length along the curve. And sure enough, this ends up becoming the derivative of the cross product of b with t by virtue of this expression right here. And this becomes then the derivative of the binormal vector with respect to arc length across the unit tangent vector plus the binormal vector cross product with the derivative of the tangent vector with respect to arc length from the product rule for the cross product that we talked about last lecture. And what's nice in the reason that we started with the first two equations is that this equation reduces as follows. The last equation, we saw that the derivative of the binormal vector with respect to arc length is just the torsion times the unit normal vector. And we saw that the binormal vector here, so we cross with the derivative of the unit tangent vector with respect to arc length, which is just the curvature times the unit normal vector. So we can simplify this a little bit more. So the rate of change of the unit normal vector is going to be this tau times n hat cross t hat. And then it will be kappa is the curvature, times b hat cross n hat. And luckily these things are not too difficult to figure out because we are in an orthonormal frame. So remember the properties of the cross product. If b hat is t hat cross n hat, then n hat cross t hat will be negative t hat cross n hat or negative b hat. And same thing with these two expressions right here, right? But b hat cross n hat is now going to be negative t hat. The final expression that we have is that dn hat ds, the rate of change of the unit normal vector, is going to be negative kappa times t hat minus tau times b hat. And this third equation that we've derived is actually what's called the second Frenet formula. And now we'll actually see why this is the nicest way of writing these three formulas. So if I take on the next page and copy each one of these formulas that we've derived, you will hopefully see the beauty of what it is that we've done. So we've clearly, without a shadow of a doubt, shown the following. I'm going to remove the functional dependence here, but remember that both torsion and curvature, so both kappa, so curvature, and torsion, tau, are functions of arc length. So they are changing along the curve as you travel on the curve. But what we've done is we've derived what's called the Frenet-Serrat system of differential equations. And the left-hand side are first-order derivatives. For each one of these has 3 first-order derivatives. And the right-hand side, we just have the functions themselves. So n hat, t hat, b hat, and n hat, along with the curvature function and the torsion function tau. This is called the Frenet-Serrat. Formulas or system of ODEs, or ordinary differential equations. And this is remarkable because this is a system of ordinary differential equations that essentially govern any parametric curve in 3D. If you have the curvature function of the curve and the torsion function of the curve, that this curve obeys this system of ordinary differential equations. Specifically, the Frenet frame obeys this system of differential equations. And it is a relatively large system of differential equations because you have 3 equations here, 3 equations here, and 3 equations here, which gives you a total of 9 equations. But it is a linear system of ordinary differential equations. So this will be an interesting thing to look at a little bit later on in the course when we get into systems of ODEs. So how can we use this? Well, I guess the first thing we should look at is if we have a curve that's parameterized by arc length. So consider a curve C that is parameterized by arc length S, So the position vector of the curve is some function, the vector function of S, which is arc length. Recall that we've calculated and shown that the unit tangent vector t is just equal to the S derivative of position or the derivative of position with respect to arc length along the curve, and we'll use the prime notation to simplify this. So prime in this case is going to mean derivative with respect to S, just to simplify calculations. Furthermore, remember that we define the curvature of a curve, the curvature function at any point, to be the magnitude of the rate of change of t with respect to S. And because t is the first derivative of our position with respect to arc length, this is the same thing as saying that it's the magnitude of the second derivative of position with respect to arc length, or just r prime prime for short in this notation. Also recall that we defined the unit normal vector to be the unit vector pointing in the direction of the rate of change of the tangent vector with respect to arc length. Which is the same thing as 1 over the curvature function times this derivative, or the second derivative of r with respect to S divided by the curvature. What we showed before, the curvature is just the magnitude of this numerator vector. So in short, n hat, the normal vector, is just r prime prime over the magnitude of r prime prime. You'll remember that r prime prime, again, the double prime here denotes the second derivative with respect to S, the arc length of the curve. And lastly, we have that b hat, or the unit binormal vector, was equal to t hat cross n hat, which again we can re-express as that the first derivative of r with respect to arc length cross the second derivative of r with respect to arc length divided by the magnitude of this vector. So the question is how to find the formula for torsion. It just depends on the derivatives of r with respect to arc length S. So we can use all the stuff that we've derived so far, the specifically the Frenet-Serrat formulas to do this. First things first, we consider the Frenet-Serrat formula. For the derivative of the first Frenet-Serrat formula, recall that the normal vector, this normal vector, and specifically this, the S derivative of the unit tangent vector is equal to the curvature times this unit normal vector. So if we take the second derivative of this expression, or the S derivative of this expression right here, which is the second derivative of the unit tangent vector with respect to arc length, that means that the second derivative of the unit tangent vector with respect to arc length along the curve is going to be the derivative of kappa times n hat which will end up being the derivative of kappa times n hat plus kappa times the derivative of the unit normal vector with respect to arc length. That's the second derivative of the unit tangent vector with respect to arc length. It's equal to this. And we can go through and actually simplify this a little bit more, because remember from the second Frenet-Serrat formula, this expression right here is equal to we have here kappa prime n hat plus kappa. So this derivative right here from the second Frenet-Serrat formula will be negative kappa times t and then minus tau times b. This is our first simplification here. And then if you recall that we can go through and take the cross product of this entire thing with respect to t hat. It's going to simplify a little bit. And it's going to simplify in the sense that this t hat cross t hat is going to be 0. We can also simplify this a little bit more by noticing that t hat cross n hat is just equal to b hat and negative t hat cross b hat right here is going to be equal to n hat. So if in my last step here I take the dot product of this entire expression with n hat, I will end up getting K prime, or kappa prime, n hat dot product with b hat plus kappa tau n hat dot product with n hat. And n hat dot with b hat goes to 0 because the dot product is 0, and n hat is a unit normal vector, so this goes to 1. And what I'm left with is the equation that kappa times tau is equal to the dot product of n hat with t hat across the second derivative of t hat, or the curvature is equal to this in the numerator divided by the curvature kappa in the denominator. And if you recall from what we wrote down at the very beginning, which is the relationship between the derivative of the position vector with respect to arc length and all of these unit normal vectors, so t hat, n hat, and b hat, we can directly plug in and obtain the following expression. N hat, remember, is the same thing as r double prime over the magnitude of r double prime so it's the dot product of this vector with r prime cross product with, this is r triple prime, the third derivative of r with respect to arc length. Because remember, the t hat is r prime, or the first derivative of r with respect to arc length. So the second derivative of t hat with respect to arc length is actually the third derivative of r with respect to arc length. All of this is divided by the magnitude of the second derivative because of this curvature right here. So what we've shown is that the torsion is the second derivative of position with respect to arc length dotted with the first derivative of r with respect to arc length cross product with the third derivative of r with respect to arc length, all divided by the magnitude of the second derivative squared, or the second derivative dot product with itself. And we've obtained a very nice formula for torsion. And one of the key things that we want to note here is that the torsion specifically depends on all three, the first three derivatives of position